I thought this was the main part.
Okay, so we went through this series last time. The right side is a geometric series with the first term 1 and common ratio x. So if you use a over 1 minus r, you get this. Now from this, you can figure out what the Taylor series of 1 over 1 plus x is. What would that be?
1 minus x squared.
Yeah, so you write it as 1 minus negative x, and then you think about this right side as x replaced by negative x, right? So it would be 1 minus x plus x squared minus x cubed plus x to the fourth minus x to the fifth plus da da da. Okay. Because if you take negative x to the odd power, you still have a minus. However, if you take negative x to the even power, the negative sign goes away, right? Okay, so using that, I want to try to solve the following question. So last time we did the Maclaurin series of x times cosine 2x. So this is our next question. Find the Maclaurin series of f of x equals to ln of x plus 1. And already in the first example, I showed you how useless this formula is, right? So an equals to 1 over n factorial, f differentiated n times, and you plug in 0. Seems like an easy formula to figure out the coefficients, but it's not very good. We'll try to do that again and see, once again, it's not very good. However, before I start doing this, let me give you some more context. See, I told you the Taylor series of sine, cosine, exponential function, and even this function. So 4 of them I told you to memorize, right? Now, that naturally raises questions like, what about tangent? What about logs? What about cosecant and all that? Now, as far as trying to get the approximate value of these functions using the Taylor series, the tangent and cosecant, these are okay because they can be all obtained by knowing the values of sine and cosine, right? However, when it comes to logarithms or even inverse trigs, those are harder, so you probably want to get the Taylor series for these separately. So that's why we want this. Okay? So this is like a natural question to ask. Now what's unnatural is you probably are thinking like you want to know the series for log of x. Why am I putting plus 1? That would be like a natural question to ask. Do you know why? Why would it be?
Could you break it up then?
No, you can't. This is not the same as log of x plus log of 1. So the short answer is this. Suppose we really wanted the Maclaurin series of log of x. Then let's say we use this formula. Let's say we want a1. What is it? 1 over 1 factorial, and then you differentiate this and you plug in 0, right? What do you get if you differentiate?
1 over x.
And then what do you get if you plug in 0? It doesn't work, okay? So that's like a short answer, but there's another reason why. It's obviously impossible because the graph of log of x is this. It has a negative infinity as the limiting value at 0, near 0. And what does the Maclaurin series do? It gives you a polynomial approximation of the function near 0. So there's no way to approximate the logarithmic function at 0. And that's why we are doing log of x plus 1. Because log of x plus 1, what happens to the graph? It moves left by 1 step, right? So if you take this and you move it by 1 step, you end up with this. And now it's possible to have an approximation near 0. Okay? So that's why we want log of x plus 1. Okay?
So then what would you do then?
Hmm?
What's the graph of e then? Does that start at 0, right?
Oh, you wanted the graph of e to the x? E to the x is like that.
Oh, so then wouldn't we have to move it down one? Or something?
No. this one we had the Taylor series without any problem because it's near 0, so there's a polynomial that approximates this 0.
Oh, okay.
So that there was no problem there. The issue was that logarithm goes to negative infinity. So e to the x has a horizontal asymptote. Logarithm is the inverse of e to the x, so it has a vertical asymptote. Horizontal asymptotes are okay.
Oh, okay.
Vertical asymptote is the one that causes the problem. Okay. All right. So let's try to do attempt 1, just like last time. The unnecessary attempts, because we're so much of a fan of any formula. You think, oh, you learned something and they give you a formula and that should be like your savior. Every question should be solved by the formula. Unfortunately, that's not true in this case. But nonetheless, let's still try, okay? So what is A0? A0 is 1 over 0 factorial f differentiated 0 times, so it's just f itself, and then you plug in 0. What's 0 factorial? 1. So it's 1 times f of 0, but what's ln of 0 plus 1, or ln of 1? What's that? 0. 0. Ln of 1 is 0, right? Okay, and then a1 is 1 over 1 factorial f differentiated once, and you plug in 0. Which means, again, this is 1 over 1 factorial is just 1. And if you differentiate this, this is 1 over x plus 1. This is the derivative of this. And then you plug in x equal to 0 in there, so you get
1.
1. Okay. And then a2 will be 1 over 2 factorial, f differentiated twice, and then you plug in 0. 1 over 2 factorial is 1/2. If you differentiate this, that's negative 1 over x plus 1 squared. Well, it's either by the quotient rule, or you can use the power rule by writing this as x plus 1 to the negative 1 power. Okay?
You plug in
And then you
1.
plug in x equal to 0, right?
No, it's 0 again? Okay.
Yeah, it's always, that's the formula for Maclaurin series. You always have to plug in 0. See, for Taylor series, if you expand with the center at 1, then you would plug in 1 there. Okay?
So A2 is negative 1/2.
This is negative 1/2, okay? And then now the question is, do we want to continue doing this way?
No, because you're
No,
showing the circle.
it's just too much, right? Now, this is slightly better situation than the x times cosine 2x case, the first example that we did. Over there, like, it was impossible to get any kind of pattern out of those calculations. This one, if you're patient enough and you do a few more terms, you will find some pattern and you'll be able to get the answer. But if you're patient, you can do it this way. Now, the second attempt, so out with this formula, it's useless, right? Now, the second attempt is to use something that we already know. And why would I have brought up these two things? Because one of them is related to log of x plus 1. Which one? Which one is related with log of x plus 1?
The bottom.
The bottom one. Why? What relation does this function have with this function?
Well, because A1 derivative.
If you differentiate log of x plus 1, you get 1 over 1 plus x, right? Therefore, if you want log of x plus 1 from here, what should you do?
Rewrite it.
You integrate, right? So you say, I know that 1 over 1 plus x is same as 1 minus x plus x squared minus x cubed plus x to the 4th, da da da, and then you integrate both sides. And the left side turns into ln of x plus 1. Oh, I should be writing 1 plus x, but addition is commutative, so it doesn't matter if I write 1 plus x or x plus 1. So that's what I get on the left side. On the right side, I have 1 integrates to x integrates to 1/2 x squared, plus x squared integrates to 1/3 x cubed. Oh, so do you see a pattern now? What's the next one?
Minus
1/4 x to the 4th plus 1/5 x to the 5th, so on and so on. Okay. Now, so I integrate both sides. I'm missing something. What am I missing? I forgot to
Plus C.
put plus C. Yes, plus C. Constant term. Yeah, you have to have that. Sometimes you can't, because you can't guarantee that that's 0. Now, in order to get C, what should I do?
Integrate.
You
No.
should plug in
Plug
negative
in
1.
x. No. Plug in x equal to 0.
Oh, so the, okay, so
Yeah,
that you
so
get
L,
0. Yeah.
you get ln of 1 on the left side, and then everything here goes away, and you just get C, so that C is equal to 0. Okay? That means the answer to this question is ln of x plus 1 equals to x minus 1 over 2x squared plus 1/3 x cubed minus 1/4 x to the 4th plus 1/5 x to the 5th, and so on and so on. Okay? Now, I also want you to be able to write this in sigma notation, so let's try the sigma notation. I see a 5 and then 5. So if you write a general term that looks like this, what should I write in here? 1 over n x to the n. And then n starts from where?
0.
1. It starts from 1. It doesn't start from 0. Okay? It's 1 over 1x, the first part. That's the very first term. Okay? And then you add to infinity. However, this is still not correct. Why?
Because
It doesn't, because it doesn't change signs, right? So it has to alternate signs, plus, minus, plus, minus. What should I put in order to make that happen?
negative 1 to the
Negative 1 to the nth power, right? So you put negative 1 to the nth power, but then if n is 1, then it becomes negative, but this is positive, so you actually have to fix this by putting plus 1 there. Okay? Then this is the exact representation, the exact sigma notation for this power series. Okay, a few more things. When is this valid? This very first one, which brought all this. When is this valid?
When x is not 1.
Well, when x is less than 1,
Yes.
and then bigger than?
0.
No, bigger than?
negative 1.
Negative 1. So your common ratio has to be between negative 1 and 1 in order for a geometric series to converge, right? And because here we only switched the sign of x, you just have to multiply x by negative x. So this is still true that x has to be between negative 1 and 1 in order for this to converge. Okay. And therefore, this series right here is only going to make sense if x is between negative 1 to 1. Okay? Because it came from here. Now, what is a bit of a surprise is that it actually still makes sense if x is 1. Still makes sense if x is 1. So let's talk about that. Okay? So let me write down a few consequences. Number 1, ln of any value can be computed as below. Okay, so for example, I wanted ln of 5. Now, one might think, oh, for that to happen, you should be plugging in 4 here, right? So ln of 4 plus 1, which is 5, should be equal to 4 minus something plus something. But that's no good. Why is it bad?
Because it diverges.
Because it diverges. Because we know that x has to be between negative 1 to 1 in order for it to converge. You see that? Yeah. So you can't directly use this this series. However, here's a trick. You can rewrite this as negative of negative 1 times ln of 5. Okay? Negative of negative is positive, right? And then what is this thing called?
Or you can bring it.
Frog over the log.
Frog over the log, my favorite formula for logs, right? Okay, so this can jump over the log and lodge it here. So it's negative ln of 5 to the negative 1, which is negative ln of 1 over 5. Right? And, well, how do you get 1 over 5? You have to plug in negative 4 over 5. Right? If you plug in negative 4 over 5, so this is going to be negative of ln of negative 4 over 5 plus 1. And then you can get negative of negative 4 over 5 minus 1/2 negative 4 over 5 squared plus 1/3 negative 4 over 5 cubed, so on and so on. Okay? So it's possible. You can do it that way, right? Now, number 2, amazingly, ln of 2, of course we can compute ln of 2 this way as well. You can rewrite this as like negative ln of 1/2 and then figure out what x has to be in order to get the ln of 1/2. You can do it this way. However, we can just simply say this is ln of 1 plus 1. And then, because x is 1, you can just write down 1 minus 1/2 plus 1/3 minus 1/4 plus 1/5, and so on and so on. Okay? And then if you compare this value with the ln of 2 approximation that you got it from this other method, you're going to see that they agree. In other words, this series, although a priori it should be only working on here, it actually works when x is 1 as well. Okay, so in other words, the Maclaurin series gives the correct value of ln of x plus 1 for this interval, x between, well, we already knew that it should be true for here, but it actually includes 1. Even 1 is okay. Now, you might wonder what happens if you plug in negative 1 then. Well, if you plug in negative 1, then the left side is not defined, because what is ln of negative 1 plus 1? That's ln of 0. What's ln of 0?
1.
No.
Oh, 0.
I gave you the graph, right?
Oh, it's infinity.
Negative infinity. So we know that the value of the left side doesn't work anyways, so there's no way to plug in something that's negative 1. Negative 1 is not allowed at all. And in fact, if you plug in negative 1 on this right side, you will see that does converge to negative infinity. So, so that's another thing that you observe.